Good evening, this is Tommy Maldonado. This is my Calculus 3 extra credit project. Um, I ask that you forgive me if this is a little unprofessional. Um, I'm just using the resources I was given. The function that I chose was function number 19. It is the natural log of 1 plus x squared plus y squared times the natural log of 1 plus z squared. The domain given to us was x being bounded above by 0 and unbounded below, y being well, this is wrong. X is supposed to be greater than or equal to 0, and y is supposed to be less than or equal to 0. Forgive me. And z is going to be bounded between 0 and 2. Now, the range, I went ahead and solved for it. It's x squared plus y squared is greater than or equal to 0. This is true for all real values of x and y. And then we add 1 to both sides and find the natural log of both, and we find that the first term being ln of 1 plus x squared plus y squared is always going to be greater than or equal to 0. And that's what I put there on the right. And for all other values of x, given our domain, it's going to be extending towards infinity. And with the z value, it's going to be between 0 and ln of 5. Let's just plug it into values. And so therefore, the range of the function is going to be from 0 to infinity. The surface behavior of the graph is that on the xy plane it is actually symmetrical, radially symmetrical, and the z-axis only affects the vertical stretch of the function. So finding the level curves and the slices, I set the function equal to some arbitrary value c, and then I set the z term towards another arbitrary value I called it a, and I solved for the function by dividing by a, so we get c over a, and then solve for x squared plus y squared. And this gives the level curve. And then down here I have the slices where we set each value separately equal to 0. The first one there is setting z equal to 0. Doing this finds that the function is centered at the origin. And then over here on the bottom is where I set y and x separately equal to 0, showing that they are very similar in their behavior and proving they're symmetrical. Okay, now for the partial derivatives and the critical points, I have here the first orders. Um, it's just a simple chain rule derivative for all three of them. Here I have the second order derivatives, and this one was a little more difficult. I had to use the quotient rule in order to find them. Now, here are the critical points and the second derivative test. I set each numerator for the first order partial derivatives equal to 0, and found that at f of 0, 0, 0 is the only critical point on the function. And with the second derivative test, when we find every single one of those second order partial derivatives, we find that at the critical point each of them are equal to 0, making the test inconclusive. The gradient and field vector. Now the gradient is just the first order partial derivatives as a set of components, which I've set there. And what this shows is that the gradient points away from the origin in the xy plane and in the positive z direction. So it doesn't go any lower in the z direction, it's always going to be above it. And the x and y increase away from the origin in a positive direction. And the Lagrange multiplier wasn't necessary because the only extrema that occurs in this function is that f of 0, 0, 0, which makes it a global extrema, is a global minimum. This is a triple integral, and what I did here over there on the right is I separated the triple integral into a single integral with the z component, the z term, because it's the only one being affected by the z, and I multiplied into a double integral, making it easier for me. Down there I showed on part A, solving for the z term from 0 to 2. It's a pretty standard integral. I said u equal to n. It's pretty standard integration by parts integral. Um, it's pretty standard integral by parts integral. Okay, now for the second part of the integral, I got a part B. I went ahead and switched it to. I went ahead and switched it to. I went ahead and switched it to polar coordinates because I tried solving it using Cartesian coordinates, but it is super lengthy, and I was not going to do that. And this just made it way easier. Um, so x squared plus y squared equals to r squared, the standard stuff, and I have r being from 0 to infinity because the x and y values are unbounded, and theta between 3 pi over 2 and pi over 2 because given the domain, this is going to be set in the first and the fourth quadrant. I used the u substitution to solve for this one, and towards the end I did change the bounds for the integral from infinity towards a c because it is an indefinite integral, and at the end there I set the limit as c approaches infinity and found that it is equal to negative 1 over 2. Then I integrated again for the theta portion and found that this portion of the integral is equal to pi over 2. And finally, here at the end, I went ahead and multiplied them together to get the final answer. And this answer gives the volume given the domain, which was x is greater than or equal to 0, y is less than or equal to 2, and z is bounded between 0 and 2.